This video is two-sample hypothesis testing for paired samples and also confidence intervals for the difference in two populations. So we've talked about comparing two sample means and two sample proportions, but we're also going to talk about something called paired samples. Listen to the following scenario. A mechanic wants to know if a tune-up will improve gas mileage. The mileage in miles per gallon was found for each of 8 automobiles. The mileage for each vehicle was found a second time after the tune-up was given. The table below shows the mileage for each car before and after the tune-up. So we have 8 cars, 1, 2, 3, 4, 5, 6, 7, 8, and we have their after tune-up mileage, and we have their before tune-up mileage. And we would like to determine if the population mean mileage is higher after the tune-up. So this is considered a paired sample because each value before tune-up is paired with a value from the same car for after tune-up. So this is when we our samples are directly related. Each data value in the first sample is related to a specific data value in the second. Okay, they have to be that related, like husband data and wife data, before and after data, brother sister data, things that that can be paired up, like the individual data values from one sample are paired with another, like this 35.44 is paired with the 33.76. Okay, so because the data values from each sample are paired, we can't just run a two-sample t-test to compare the means. What we need to do is we need to see if there's a change from the before the tune-up to the after the tune-up. We need to see if there are any differences in relation to each specific car. So we need to find the differences for each specific car, and then you can find the mean of that and run a test on that. So now the direction you subtract just depends on how your data is presented and also how your claim is worded. In this case, let's see what it said. We wanted to know if the population mileage is higher after the tune-up. So they also gave us the after tune-up data first. So what that means is the after tune-ups numbers should be mostly higher than the before tune-up numbers, if that was the case. So when we write our null and our alternate hypothesis, we're going to use slightly different notation because we're interested in those specific differences. So for the null, we're going to assume there's no difference as usual, but this is how we're going to write it. We're going to write mu d equals 0. D stands for difference, so the mean difference is 0. So if we're going to assume that there's no difference, that's how we would write it. We will not write mu1 equals mu2. We will write mu d equals 0. And for the alternate, we will write either mu d is less than 0, mu d is greater than 0, or mu d is not equal to 0. So the steps for the paired sample hypothesis testing, it's mostly the same, but a little bit different because we have to take those differences. So first you want to state the null and the alternate hypothesis. And we already talked about that. You are going to put your data in L1 and L2. Just be careful, pay attention to which one is L1 and which one's L2. And then in L3 you're going to find the difference in L1 and L2. Sometimes we will do L1 minus L2, and sometimes we will need to do L2 minus L1. It just depends on how things are worded. Then we're going to run a t-test. Now we've run a t-test before, back when we were testing one sample, but what happens here is we're just running a test on the differences of the data. That's why we don't need a two-sample t-test for two samples, because the data we're actually using is not the data from sample 1 or sample 2. We're using the data of the differences of those two samples. So it's actually just one list of data. And we put that in L3. We actually have the calculator calculate it for us, and we run the test choosing data as the option And then we run the test on L3 if that's where we put our differences. And then we compare the p-value as usual. And then we make the decision to reject or fail to reject the null, and we write our conclusion in context of the problem. So much of it is the same. The biggest differences are the way we write our null and alternate hypothesis, comparing it to 0. And then we are having to enter our data into 2 lists and then find a difference. So make sure you remember that. So going back to the original problem, I'm going to reread it. A mechanic wants to know if a tune-up will improve gas mileage. The mileage in miles per gallon was found for each of 8 automobiles. The mileage for each vehicle was found a second time after a tune-up was given. The table above shows the mileage for each car before and after the tune-up. Can you conclude that tune-ups improve mileage? So if they improve mileage, that means that the after is going to be greater than the before. If we're improving the mileage, that means we're going to get more mileage, so it's going to be greater. So how would we write that? So first off, we recognize this is paired data because it's for 8 individual cars, and we've taken two sets of data from the same sample. So our null is the mean difference is 0. We're saying there's no difference. The alternate statement, we need to decide how we're subtracting. Are we subtracting after minus before or before minus after? And this really matters. The reason it matters is because if I subtract after minus before, according to what I want to see that this is greater. After minus before means I should get, if this is really greater, I should get positive numbers. If you subtract a bigger number minus a smaller number, you get a positive number. So in that case, mu d should be greater than 0. But if I subtract before minus after, we would be saying we're subtracting a smaller number minus a bigger number, and in that case we would get a negative number, which would be less than 0. So it really all depends on the setup and which one you're going to subtract, L1 minus L2 or L2 minus L1, so just be careful there. But I'm going to leave this one as L1 and this one as L2, so that when for L3 I'm going to do L1 minus L2 after minus before, and I should get a number greater than 0 if this claim is true. Okay, so let me go back there and pull up my calculator. Alright, so what I'm going to do is I'm going to go and I'm going to go into my lists and clear them out. And I'm going to put my data. It is very important that your data gets put in the same order that it's given in. You'll also notice for this type of data that all the sample sizes will be the same. You will have the same number in the first sample as you do in the second sample. Oops. Let me just go back and make sure I've typed these in correctly. 32.39, 25.18, 23.11, 26.48, 31.57, 31.07, 35.17, 35.44. Alright, I'm entering L2. Let me just go back and make sure I have 8 in both, 31.25, 24.30, 21.78. Oops, I forgot a decimal there. 24.92. That would have thrown everything off. This is why I check. 30.90, 29.55, 34.30, 33.76. Alright, so what you're going to do is notice how I highlighted L3. Whenever I moved it over, it was right there. See how it's highlighting here? And I move the arrow up. So I'm highlighting L3. And now I'm going to type in L1 minus L2. So second 1 minus second 2. That's because I want to do after minus before. And here we go. And it looks like we're getting all positive numbers. So that bodes well for the claim there. But we still need to run the test. So we're going to go to Stat, Tests. We're going to choose number 2, t-test, but we're going to choose data. Make sure you choose data. Your null, mu0, will always equal 0 because it's going to match what we had here. Your list, make sure you put in L3 or wherever you put the differences. So I'm going to do second 3. Frequency should stay the same. We're trying to say that the after is greater than the before. And I'm going to calculate it. And it looks like I get 1.9 blah 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 e to the negative 5. 1.9 e negative 5. So that's 0.00019. The 0 looks at the 1 and stays as 0. So my p-value is 0, which is less than 0.01. So we're going to reject the null. So we can conclude that tune-ups improve mileage. All right, example 2, brake pads. For a sample of 9 automobiles, the mileage in 1,000s of miles at which original front brake pads were worn to 10% of their original thickness was measured, as was the mileage at which the original rear brake pads were worn to 10% of their original thickness. The results are given below. So we can see that because these are for the same 9 cars, the rear versus the front, that we're comparing, this is paired data. So can you conclude that the mean time for the rear brake pads to wear out is longer than the mean time for the front pads? So why don't you pause the video and attempt this, and then we'll come back and we'll see how you did. Okay, for the null, we did mu d is equal to 0 and mu d is greater than 0 for the alternate statement. For L3, I did rear minus front, L1 minus L2. And because we were saying that it's longer, that's why I chose greater than, because if rear is longer, when I subtract, I'll get a positive number, which is greater than 0. P-value, if I entered everything in the calculator correctly, hopefully I did, I got 3.188 e negative 12, which is 0. 0 is definitely less than any significance level they gave us. They gave us 0.05. So we rejected the null. So we can conclude that the mean time for rear brake pads to wear out is longer than that of front brake pads. Hypnotism. A study was conducted to investigate the effectiveness of hypnotism in reducing pain. Results for randomly selected subjects are shown below. So we have the subjects A through H, and then the before and the after, so you can tell that it's paired. A lower score indicates less pain. The before value is matched to an after value, and the differences are calculated. Actually, the differences are not calculated. The differences have a normal distribution. Are the sensory measurements on average lower for hypnotism? Lower after hypnotism. Test at 5% significance level. So pause the video. This one you might want to think about the order that you put things in, but pause the video and come back and see how well you did. Okay, for this one we wanted to know if it was lower after hypnotism, so I left it L1 and L2 for the first and the second, but if it's lower after hypnotism, then if I subtract after minus before, I should get less than 0. So I did L2 minus L1. If you did L1 minus L2, you would need to change that to greater than. But I wanted to keep it with the wording since it said lower, and I think less than kind of goes with lower. That's why I did it this way. I put my data in L1 and L2. In L3, I did L2 minus L1. The p-value that I got was 0.0095. That's less than the significance level of 0.05, so we rejected the null. So we have enough evidence to conclude that sensory measurements are lower after hypnotism. Okay, so we're going to stop here and pick up with part 2.